Okay, in this video we're going to be covering physical and chemical changes. You do have another PowerPoint in the drive that maybe goes into more explanation. The purpose of this video is to give you a bit more minds-on about how to relate the different terms together and to use them in a few kind of unique scenarios. So first thing we want to do is just quickly review properties. In this example, we have 4 different students. And let's review their physical properties. So for this first individual, we could say a physical property of color. They would have a red shirt and brown hair. For the second student, again, you can use color and say green shirt, and you can use age, 15 years old. And this individual, you can use shape, so they're slender, or you can use smell, so they smell like lavender. And then this last individual, you can do stuff like length, so short hair, and maybe he only has 8 fingers. Why? Who knows? So those would be physical properties, things we observe directly with our 5 senses. Then when we talk about chemical properties, and when you look at chemical properties, it's how matter interacts with other matter. So for this first individual, in this case, how the students would interact. So this one, they interact well with other students. You know, they play nice. This individual, they do well when they're close to the teacher. So it doesn't matter what student they need to, but if they're close to the teacher, hey, they do pretty good. This last student, or sorry, third student, does not interact at all with other students. It's not that they're good or bad, they just don't interact at all. They will not play or interact with other students. And then this last guy, very loud and distracting around other students. So I know I have 10 fingers, so this isn't me, but this bottom part would probably describe me. Very loud, distracting around other people. So here you go, some basic chemical and physical properties. So hopefully that's a bit of a review. And I hear Miss Engelhart chuckling in the background because she knows this is
Yep.
true.
Oh, it is very true.
Yeah, don't sit near me in the staff meeting. You'll never get to hear anything. All right. So seating plans, always a teacher's worst nightmare. Me, I usually just let you come in and sit down. If there's a problem, I move you. But if there's ever going to be an argument in the classroom, it's usually over trying to move you or taking away your phone. But yeah. So let's say I have this seating plan. You know, the red shirt and the green shirt sit next to each other, and then the 8-fingered boy and the girl that smells like lavender sit near each other at the front. Now, let's say I was to go ahead and change where they're sitting. So now I'm going to put the 8-fingered boy at the back with the red shirt boy, and then the green shirt kid gets to sit with the slender girl at the front. Okay? And there's me at the front. So do we have the same people in the classroom? Well, the obvious answer is yes. So if we're thinking about students being matter, we have the same matter in the room. We haven't changed the people. Do we have the same desks? Well, look at the pictures. Yeah, we have the same desks, of course. So what's different? If you need to, pause the video for a second and think about it. Did we change any physical properties, chemical properties, or both? So we will give you a clue to this later. So what has changed? Well, we have the same elements in the room. Properties have changed. So physical change and properties changed. Just some definitions. If you want, you can write them on a piece of paper. If not, you can check out the PowerPoint. In a physical change, the form of the matter has changed, but it remains the same substance. So if I have water at the start, I have water at the end. When a chemical change, when one or more substances changes into one or more new substances. So let's say I have some oxygen gas and some hydrogen gas, I mix it together, now I have water. In both cases, I have the same elements involved, they're just not put together in the same way. So in a physical change, some properties have changed, chemical and physical properties, and the same thing goes for chemical changes. We're actually changing chemical and physical properties. So a physical change isn't just a change in physical properties, or the same thing with chemical changes. Okay? So some examples for physical change are splitting wood and melting an ice cube. And some examples for chemical changes are lighting a log on fire or curdling milk. All right, let's take a look at the first one. Melting an ice cube. So let's put a picture of ice cube up there. Not sure that's the ice cube we're going for. Okay, so yeah, okay, that's the ice cube we're looking for instead. And there's what it changes into. We are melting it and turning it into water. So physical properties would be that it's solid. It's 0 degrees Celsius, right? That's shape and temperature and state of matter, low viscosity. So, I mean, an ice cube doesn't really flow at all. Properties, it's low flammability. It's hard to, really hard to light on fire, and it's really hard to keep on fire once it is on fire. I mean, it's water. Okay, but it does react with acid. So those are the chemical properties. And let's look at the chemical and physical properties of water. Well, let's see, it's liquid. It's, let's say, 15 degrees Celsius, very high viscosity, and it flows really easily. But it still has a low flammability and a low combustibility, but it can still react with acid. So if you notice here, we've changed some physical properties, but the chemical properties are the same. Is it still the same stuff? Did I have H2O before and H2O after? What's the answer there, Ms. Engelhardt?
Yes.
Okay, so yes, it is still water. So this is a physical change. We've only changed the things about it, but it is still the same thing. All right, next example. A log and a matchsticks. There's a giant log, and there's tiny little matchsticks. All right, physical properties. Well, 10 meters long, 1 meter in diameter. I mean, you could describe color, you could describe all kinds of other things. Fine. Chemical properties. Well, it's very low in flammability. It's very hard to light that log on fire. However, when we get it on fire, as long as we keep adding some heat, it'll stay on fire. So it's low flammability. It won't light on fire easily, but it is combustible. It will stay on fire for a long time. Okay. Physical properties of the matchsticks. Well, they're 10 centimeters long, half a centimeter wide, quarter of a centimeter in height. Okay. But when I change the size of the matchsticks, they now become highly flammable. These things are now easy to light on fire. But they have low combustibility. They light on fire easy, but they don't stay on fire for very long. They actually burn out really fast.
And then burn your fingers while you're holding them.
All the time. Why use a barbecue lighter in the lab, not a splint anymore? Because I've done it too many times. Yeah. So by changing a physical property, we've actually changed chemical properties as well. So you can see we have two examples where we've changed physical properties and the chemical properties don't change. And then in this case where we change physical properties, it completely changes the chemical properties. But the question is at the end, what do we have before and what do we have after? It is still the same stuff, right? It's still wood. So it's a physical change. Even though the chemical properties might have shifted, and we've changed both physical and chemical properties, it is still a physical change. Okay? You got to make sure you separate physical and chemical properties with physical and chemical changes. They're not the same thing. Okay, third example. Lighting a log on fire. So now that we've cut up the logs into like a medium size, we're going to then use them in our little fireplace here. So physical properties, again, I'll throw them up. You know, the logs are bigger. Well, they're the exact same size as the one that's in the fireplace, except in the fireplace now, maybe they're a little bit smaller because they've started to burn and they're eventually they'll disappear, right? So this is maybe a log that's been on fire for 20, 30 minutes. But we went from having just wood to now having 3 different materials in there. We got wood, ash, and also gas. Well, let's look at chemical properties then. This is, you know, low flammable, medium combustibility. Okay. That stays the same for wood in both cases, but now we have to put the properties for the other 2 materials, which ash would react, let's say, with acid, and gas would react with water to make an acid. Okay. So in this situation, we went from having like just one thing, wood, to having multiple things afterwards. So, what would that be? Do we have the same stuff? What do you think, Ms. Engelhardt?
No, we don't.
Oh, so then what would that make it then?
So that would have to be a chemical change because we have new things.
That's right. So you started with wood, now you have wood, ash, and gas. It is now a chemical change. It's no longer the same matter. Now remember, just like the kids sitting in the room, we still have the same kids before and after, so keep that in mind for this example. Even though we have different things, it's Just follow along. So the question is there a quick way to tell the difference between physical and chemical, or do you changes, or do you have to make like a chart like I just did and always put it out there? Well, luckily for you, yeah, we will diagnose a physical change by the process of elimination, which means we will see if it's chemical, and if it's not, we will say, hey, must be physical. Okay. It's like when you go to the doctor and you say, my head hurts, and they check you for concussion, they check you for all kinds of things, and if they can't find anything, they say, hey, you'll be fine, it's nothing. Okay? It's by the process of elimination that you diagnose. So we have some very, very good clues to chemical change. And the first one is heat or light is given off. So the example of the log, we're giving off both light and heat. If you turned off the light with a log in your room, nothing happens. You light it on fire, well, you're gonna have the heat and light there, right? So that's a very, very good clue. Now, it doesn't have to be fire. It could, let's say, be glowing. Think of a light bulb. It's not on fire, but it's glowing. Second clue, there's a change in color. More importantly, a new color appears. So if I mixed yellow or white paint and red paint, I would get what color? Pink, right? Yeah. Well, if I mix red paint and white paint, am I actually getting a new color, or is it just both colors were there before and they've mixed and I got kind of the average? It's the average situation. This is talking about a new color, something that wasn't there before. So the nail previously was this nice gray. I exposed it to clear gas, oxygen, and all of a sudden I start getting this reddish tinge to it, in this case, rusting. So you have to have a brand new color appear, a color that wasn't there before. It's not a blend of previous colors, it's a new color. So when we say color change, we actually mean a new color. The third one is you get bubbles or gases given off. Now, don't confuse this with having, like getting a bucket of water and stirring it really fast and then seeing bubbles in the water. You stirred them in, you just created a mixture. This is when you put liquids together, metals together, and there wasn't bubbles before, you're not like stirring in air, and all of a sudden you start getting bubbles coming off of it.
What if you heat a pot of water?
That's a good question. If you're heating a pot of water, what would that be? Physical or chemical?
It'd be physical.
It would be, yeah. So this is why sometimes it's hard to tell. Right? Now there is a way in the lab to test to see what gas is being given off. We can then go ahead and capture those bubbles and then test to see if they're both hydrogen or oxygen gas or other gases, and we can actually do that test. We'll do that test in grade 10. But yeah, that's a very good question. This is why sometimes it's kind of hard to tell here. The pot of water, you actually have a convection, and it's actually just trapping the air as it's kind of turning over. So very good question. Do you have a better way of explaining that?
Well, you could test it for water because it would still be water. Like if you were to
Right.
catch the gas and cool it down.
Yeah.
Right? Like you don't even have to do a gas check. You could catch the gas and cool it down. And if it cools down back to what it was before, well, then it really hasn't changed.
So that's why when you hold the lid above it, or you cool the lid down and hold it above it, you would just get water forming on the lid, because that's what the gas is, right? Just water? Okay. Awesome. There you go. That's a good way to test that. Okay, so this one, but this would be more like when you do the whole volcano thing, where you take the baking powder, or baking soda rather, and you pour the vinegar in it and a little bit of food dye, and you get like the big giant bubbles coming up. Unlike blowing a bubble where you're just adding air into a soap and it's being caught. So you just gotta be careful. The fourth way is a solid or precipitate is formed. This is one, it's kind of hard to tell sometimes because usually the solids that form are very, very small, almost like flecks. And it's when you take two liquids, there's no solids in them all, it's just two liquids, and you put them together, and then you'll end up usually with a liquid and solids forming. I have seen situations where you put two liquids together and they become both solid. And this one, you really have to see it in order to understand exactly how it works. So in this case, we're using, I think it's sodium hydroxide and iron sulfide,
Yeah.
I think. Yeah,
Sulfide,
and you mix them together, and then the iron separates and becomes. Anyways, so what you're seeing in there is little flecks of iron. So that's basically it. You put two liquids together and you end up getting a solid coming out of it. And that would be precipitate. And then the last one is the change is difficult to reverse. But this can be the same as physical. So like when I take that tree and I cut it up into little tiny matchsticks, I'm not putting it back together as a tree. And so this is why it's a clue, right?
Or I take a pencil and I snap it into.
Yeah, that's right. Exactly. Or I cut up a piece of celery. I can't then turn it into a celery stalk. But it's still celery, right? So this is where you have to use a little bit of logic and kind of think about it. Now, the example we have here is frying an egg, but the frying the egg, we actually have other things happening too. Like we got a color change. So both the yolk and the egg white will change colors. So say we have a new color being formed. And that's why we have a little asterisk next to it, because if no clues are evident, then it's a physical change, right? And then that's what that little asterisk means, is that number 5 on its own, and even some of these on their own, is not really a good enough indicator to say definitively that's a chemical change. I mean, 1, 2, 3, 4, there's lots of situations where it's obvious that it's a chemical change, but you gotta be careful. Number 5 on its own is generally not good enough to say that it's a change. That's how I approach it when I teach it. Is that generally how you approach it?
Yeah.
Okay.
I really don't like using number 5 on its own.
Right. Yeah. So that example with the boiling water, I mean, it's easily reversed, right? So you have the air coming up out of the water, it hits the lid, and then you turn it back into water quite easily. So it's an easy change to reverse, right?
But if I open a can of pop and it starts bubbling,
you're not getting those bubbles
I'm
back.
not going to catch those bubbles back. No.
Yeah, exactly right. Okay, so hopefully you understand. So you look for these clues, and if you see these clues, then you're pretty sure that it's a chemical change. If you don't see them, well, then say it's a physical change. And there we go. So let's recap. Let's not confuse properties and changes. So properties describe matter and how it interacts with other stuff, right? So describing the matter is physical, how it interacts is chemical. Changes describe a change in the property of that matter. So it describes a change in the chemical and physical properties. Okay. So with the physical properties, you use your 5 senses. With the chemical property, it's describing how it interacts with other things, right? Other matter, or even in some cases energy, like does it react with heat or whatnot. Change is a physical change. The matter changes, these properties change, but it's still the same stuff. And then a chemical change, it's the properties change, but it's no longer the same stuff. And in order to figure that out, we use the 5 clues. So you'd use the 5 clues. If you feel there's good enough evidence to say it's chemical change, then go ahead and say it's chemical. If not, then by default, we say it's a physical change. I mean, some are obvious. I snap a pencil in half, we know it's physical right away. What you can be careful about is that physical properties does not equal chemical or physical changes, right? So physical properties does not equal physical changes. And chemical properties do not equal or does not equal chemical changes. So if you change a physical property, it's not a physical change necessarily. If you change a chemical property, it's not a chemical change necessarily. And that's kind of the moral of the story and where we're trying to head here. They do not equate to each other. Properties and changes are completely different things, completely different ideas. In fact, I think they just unfortunately named them the way they did so that it becomes confusing. Anything you want to add to that one?
Oftentimes with physical changes, it's the keyword with change. So it'd be something like a change of state, right? Like going from a liquid to a gas, it's a change of state. Whereas a physical property, you're describing what state it's already in. So kind of thinking about it that way as well.
Right, explaining it kind of cross that way too. Yeah, awesome. Perfect. So back to the classroom example. How could we tell if moving students around was a physical or chemical change? Well, there's our original class, and we moved the students here. Well, how could we tell? Well, were there any signs, right? I mean, this is obviously a physical change. Things aren't where they are anymore. We moved them. They're a different location, right? But is this a chemical change? Well, we'd have to look for some of the signs. So it can be both. So maybe you make this change and the classroom goes on and works the same way, then it would be just a physical change. But my experience is that the first thing that happens whenever I move kids around is, oh my God, sir, why do I have to move? Or, people getting all mad, or maybe they used to, be happy in class and now they're depressed, or maybe they were depressed before and now they're happy. And, you have some kids not caring, some kids just go from being really distracted to not distracted at all, or stuff like that. And so usually there's a lot of signs of a reaction happening. And so the answer is it can be both. It can be both a physical and a chemical change at at the same time. Anything to add to that one?
Nope.
Do you like doing seating plans and rearranging kids?
Only if I have to.
I always do it during this lesson, actually.
Okay.
So you guys are lucky that we're away at COVID, because during this lesson I always you come in and there'll be little nameplates on the desks and you have to move and everyone gets all mad at me, and then when I show this example here, you realize that I was kind of trolling you. Well, I hope you got something out of this and you now understand properties versus changes a lot better. If you have any questions, feel free to ask. Take care.
Bye.